Invitation. Professor, would you like to start?
Okay, thank you. So in this lecture, I'm going to talk about quantum circuits. So I already told you that the standard model of quantum computation is gate-based model of quantum computation. And the gate is a unitary transformation acting on constant number of qubits, O1 qubits. The quantum circuit is a sequence of such gates. So of course, maybe one can say that at this point, maybe one can say that's just a definition of the quantum circuit and that's the end of the story. But there is actually quite a bit of interesting work in this direction. And in the quantum computing literature, there are some gates and choice of gates that people use and the gate identities that people use. And there are some motivations behind this. And hopefully I can explain the why in this lecture. So let me remind you that what a circuit diagram is. So in the circuit diagram, how you draw this is that first of all, the direction of time is from left to right. And for each qubit, you draw a line. So if you have, let's say, 5 qubits, then you draw 5 lines like this. And on the left end, you start with some initial state. It's usually people start with like a 0 state, but you don't have to. And then you can have some unitary transformations, which are the gates. So if you have, let's say, gates acting on, say, 2 qubits, like the gates that I drew, then formally speaking, we call this as U. So U will be like an element of like SU4. And if you have like V, then V will be an element of SU2. And of course, you can write down the circuit this way. But in quantum computing, you will see that it's almost never the case that you write down like explicit like a 4x4 matrix or a 2x2 matrix. People often have a very specific set of 4x4 matrix or 2x2 matrix. And what I want to do is to explain to you what the standard set of such gates are, why people use that, and the set of identities that I think is very useful to understand these works. And again, like if you have any questions during this lecture, let me know. Okay, so let me start with a concept called universal gate set. So at the highest level, quantum computation can be thought as a unitary transformation acting on n qubits, where n is a variable number. And here's an important fact. So it turns out that you can find the proof of this fact in, let's say, Nielsen and Chuang, the standard textbook in quantum computing. But it turns out that for any unitary transformation acting on n qubits can be decomposed into a sequence of 1 and 2 qubit gates. Okay. What this means is that 1 and 2 qubit gates is universal in a sense that no matter what kind of unitary transformation you want to apply, you can decompose it into, you can build that up from 1 and 2 qubit gates. And more formally, we say that a gate set, some set of gates G is universal if any unitary transformation over n qubits can be approximated arbitrarily well using this gate set. So for example, if you use a continuous gate set, like the set of single qubit unitaries and set of 2 qubit unitaries, like obviously that will be universal. As long as you believe this fact, then you conclude that that set is universal. One thing that you might be thinking at this point is that the set of unitaries is not a finite set, like whether like 1 qubit, 2 qubit, or n qubit. It's a continuous set. So you might be thinking that quantum computing is probably analog. But I would argue that surprisingly, that doesn't seem to be the case. And the reason why that's not the case is that any element in this set can be approximated arbitrarily well by a finite set of 1 and 2 cubic gates. So even though the set that you want to ultimately generate is a continuous set, you can still approximate it as well as you want by using just a set of discrete gate set. And this is more of a side comment, but actually some of the early critics of quantum computing said, you will never be able to build a quantum computer because of decoherence, and you need to keep like exponentially many branches of the wave function very accurately, which would be very, very difficult. But now we know that this is an incorrect argument, because since then people built this theory called the theory of quantum error correction, which we will not talk about. But we know that we have a theory now which tells us that it is possible to correct unwanted errors. And when you look at how quantum error correction works, what you do is that you check whether there is an error or not. And this measurement process collapses the wave function, but not in a complete way. So it's not like you measured your entire wave function. You're measuring some subparts of the wave function. And that basically collapses the state onto some discrete set of states, okay, after which you can correct the error. And this is another sense in which quantum computing is digital. So even though you might think that it's more natural to think about like a 1 and 2 cubic continuous gates, you can do all these things like equally well just using a discrete set of gates. Okay, so but then there is a question, which is that which gate set should we choose? Because let's say I wanted reducing this continuous gate set down to a discrete gate set is like still not enough. There's like infinitely many different gate sets. So which one should we choose? Now, to answer this question one way to answer that question is that you can choose any discrete gate set. Like what these people, Hierarchy and Chuang, showed in 2001 is that with high probability, if you choose any gate set, any discrete gate set, then with high probability, that gate set will be universal, with probability 1 essentially. So in some sense, if you only care about universality, then you can just pick random gates and that's the end of the story. But there is a practical issue, namely, ultimately we want to do quantum computation because quantum computers can solve certain problems much faster than classical computers. But if you look at the hardwares that we have right now, every time you apply some like a 1 or 2 cubic gate, the rate at which an error might occur is between like 0.1% and 1%, which is very high if you think about it. And that's very high. Well, it's also in absolute numbers, but also for doing something useful. So people have like estimated very carefully like how many number of gates you need to apply to do something that is commercially useful, or even scientifically actually. And that number turns out to be roughly between 10 to the 10 and 10 to the 15. So if you apply 10 to the 10 gates with an error when the error is 10 to minus 3, the probability that an error occurs is probably going to be very, very close to 1. So that's obviously not very good. So this means that some form of error correction is absolutely necessary to do something useful. And the thing is, as soon as you accept this fact, as soon as you accept that to do something useful with quantum computing, you need the quantum error correction, then you're forced to use a very specific set of gate set. And this is because quantum error correction is compatible only with a very specific gate set. And this gate set is very cleanly organized into a framework called Clifford Hierarchy. So that's what we're going to learn about. Okay, so Clifford Hierarchy. I will first tell you what the definition of the Clifford Hierarchy is, and then I will go through some details. And then we'll get to learn some interesting properties of this hierarchy. So its name is a hierarchy, so there are many levels. So I would say at level zeros, we have Pauli matrices. So you might remember this from your quantum mechanics course in angular momentum. I'm going to review that one more time. And basically, let's say I call this as like Pauli P, P1, P2. And then level 1, which are called as Cliffords, are basically unitaries. So U such that U P1, U dagger is a Pauli. Okay, so I apply, like conjugate a Pauli by this unitary, and then I get a Pauli. So if this unitary U does that for all the Paulis, that's in the level 1. What about level 2? You conjugate, so this is still a set of unitaries. And what you do is that you apply U, P, U dagger. And what you want to get is that you want to get something that's at the level 1. So that's how you define level 2. So what about this? U, P, U dagger. And you want to get level 2. So you can define these things recursively this way. Okay, so yeah, what are Paulis? Well, you probably remember this in the following way. So you probably wrote down the Pauli X matrix as 0, 0, 0, 1, 1, 0, and sigma Y and sigma Z. In quantum information and quantum computation, we use these matrices so often, we don't actually bother writing down like sigma. So we just write them down as like X, Y, and Z. Okay, that's just so much easier because we just use them so often. And there's, of course, the identity matrix. All of these things are 2x2 matrices. And they satisfy some very nice set of properties. One thing is that they square to identity. It's something that you can check. And moreover, they anti-commit, except for identity, they all anti-commit with each other. So X anti-commits with Y, Y anti-commits with Z, and Z anti-commits with X. And they have this like nice cyclic property. So if you multiply X, Y, I get I, Z. The way I think about this is then I have X, Y, and Z. And I have this cycle. So X, Y, the next one is Z, so I get I, Z, Y, Z. I multiply them, I get I, X, and ZX, I get I, Y. But if the order is exchanged, then, for example, if I have YX, then I get minus IZ, for example. Okay. And another thing that you can check very easily is that all the eigenvalues of the Pauli X, Pauli Y, and Pauli Z operator, they have an eigenvalue of +1 or -1. So there's, how do you check that? So the easiest way is to actually calculate the eigenvalues, but I'm going to show you a trick which is much simpler. So suppose you believe that X squared is identity, which you can do just by 2x2 matrix multiplication. What you can check is that the trace of X is actually equal to 0. Why? Because diagonals are all 0, so the trace is 0. So let's see, and this actually completely determines the set of eigenvalues. Why? Because let's say with a lesser generality, I can write down the Eigen decomposition of X in the following way. So U is some unitary that diagonalizes X, and lambda1 and lambda2 are the eigenvalues of X. So X squared is equal to U lambda1 squared. And we know that this is an identity. So what does that mean? That means that lambda1 squared, 0, 0, lambda2 squared is equal to identity. So lambda1, lambda2, they're both ±1 or ±1. What about the trace of X? The trace of X, that's simply the sum of the eigenvalues. That's lambda1 plus lambda2. So you see that we cannot be in a situation where lambda1 and lambda2 are both +1 or both -1. If one of them is +1, the other one must be -1 as well. And you see that this argument applies to any matrix which squares to identity and whose trace is 0. And indeed, y squares to identity, its trace is 0. Z squares to identity, its trace is 0. So for all these matrices, you must have eigenvalues of +1 and -1 at the same time. In quantum computation, we don't have a single we have a single qubit, but we have more than a single qubit. We can have many qubits. And that's why we consider Pauli matrices that are acting on many number of qubits. These are called as Pauli strings. And I told you the definition about the tensor product. Let me just remind you what that is. So let's say I have P1 tensor Pn applied to some product state. So phi1 tensor phi n. What this is that it's simply P1 y1 Pn psi n. And the Pauli string is like a matrix which can be constructed from this tensor product formalism. And in each of these individual P1, P2, P and -1 Pn, they are either identity X or Y or Z. Okay. And if you have like two Pauli strings, let's say P1 tensor all the way to Pn, then you just multiply. This multiplication also works in a very straightforward way. And therefore, you can see that these two facts hold. So P squared must be identity because, well, for example, if I just remove the prime here so that I just square the same, I square a Pauli string, then I'm going to get simply P1, P1, all the way Pn, Pn, which is simply I tensor, which is just the identity on the entire Hilbert space. So that's how you prove this thing. And we already saw that there can be situations in which, so if you have like two Pauli operators on a single qubit, they can anti-commute. So this can totally happen. But if you have a Pauli string, you can actually, you may, these things may actually commute with each other. For example, let's say I have Z tensor Z and X tensor X. And imagine I try to change the order. So this is equal to Zx tensor Zx, which is equal to minus Xz. So Z and X anti-commute to each other. So that's why I have the minus sign and minus Xz. So I get -1 square Xz tensor Xz, which is X tensor X times Z tensor Z. So you can see that when we have, let's say, so in this case, we had two pairs of Pauli matrices, both anti-commutating each other. So you get -1 square, so 1. So that's why these two Pauli matrices, actually, these Pauli strings, actually commute with each other. And another neat thing is that I will argue that any Pauli matrix, which is not an identity, must also have eigenvalues of +1 or -1. And actually exactly half of them must have an eigenvalue of +1, and exactly the other half should have an eigenvalue of -1. Why is that? So I showed you that p squared is identity. So let's say, without loss of generality, suppose I have an eigen decomposition of p as λ1, lambda, let's say big N, U dagger. So p squared equals identity means that λ1 squared should be equal to lambda squared equals to lambda n squared should be equal to all 1. And therefore, all these lambdas, they must be either +1 or -1. But the thing is, trace of p is equal to 0. And why is that? It's because, well, I'm assuming that p is not an identity, but that's because, think about the definition of the trace. What you do is that you sum over some basis state of your choosing, and the basis state I'm going to choose is simply going to be the tensor product basis state. So this is simply trace of P1 times trace of P2 times the trace of Pn. And therefore, unless all of these things are identity, at least one of them would have to be 0. So 0 times some constant thing, that's a 0. And that is equal to the sum of all the eigenvalues. Yeah. And all of them must be either +1 or -1. Therefore, exactly half of them must be +1 and the exactly other half must be -1. Otherwise, they will not cancel out to become exactly equal to 0. So this way of thinking make things like extremely simple. Okay, so that's the definition of the Pauli matrices. This is a good time to stop and answer some questions if there's any. If not, I will move on to the next topic. So remember, we're talking about the Clifford hierarchy, and we started at the zeros level, which was the Pauli matrices. And by Pauli matrices, I meant not just a single qubit Pauli matrices, but these multi-qubit Pauli matrices, like these things. So then what we discussed, the next level. So these also have a special name. So the level right above the Pauli matrices is called as a Clifford Unitaries. And formally, we say a n-qubit unitary U is a Clifford unitary if for all Pauli matrix P, the UPU dagger is a Pauli matrix. And there are some like very concrete examples of this. But for example, let's say for simplicity, I simply consider some, let's say like a single qubit case. So in that case, we have Pauli matrix of I, X, Y, and Z. And what this means with plus minus sign, plus minus, plus minus, plus minus, plus minus. And what this means is that U, P, U dagger is, should be in this set. So in order to check if U is actually a Clifford, what you need to do is that for every single Pauli, conjugate by U. And yeah, there is a question actually. Yes?
Yes. Okay. So I have a question. So what is the special for the Pauli matrices here?
Sorry, I couldn't hear.
So you introduced Pauli matrix for the quantum gate. I'm wondering why these Pauli matrices are special in this gate.
Oh, I guess it's mainly because, let's see. So I guess my perspective, different people have different ideas, but my perspective is that, well, to do useful quantum computation, you have to do quantum error correction. And the most realistic quantum error correction method that people are thinking of allows you to perform certain gates, and the simplest gates in those quantum error correction scheme are the Pauli matrices. So that would be my answer. So it's like the simplest gate for which simplest non-trivial operation that you can apply while performing quantum error correction. I think that it is in that sense this is very special.
Thank you.
Okay. All right. So one should, coming back to this, so we define Clifford Unitaries. And for the case of the single qubit case, the Clifford Unitaries are very simple. So one can actually show that they are just generated by these matrices. So first of all, let's be clear on this. So X, so if you conjugate a Pauli by a Pauli, then that will become a Pauli. Why? Because let's say, for example, you conjugate X by X, then that's just X. So I'm not going to even write that down. What about YXY dagger? Well, Y and X anti-commute with each other. So this is simply like minus X. So you again get a Pauli with a minus sign. And also the same with Z. So the fact that these X, Y, and Z are in the Pauli, are in the Clifford is very obvious. What's less obvious is why these matrices H and S are in the Clifford unitary. Well, we can actually do some very explicit, a very simple calculation from which this fact follows very easily. So here's a few facts. So let's just do the calculation. So I'm going to conjugate X by H. But before I do that, let me first note that if we square H, that's just an identity. And this is just 2 by 2 matrix calculation. So you can check this very explicitly, but I will work this out for you. This is 2, 0, 0, 2, which is 1, 0, 0, 1, which is identity. Therefore, H is equal to H dagger. So it's a unitary that squares to identity. So HX dagger is really HXH. And after you do the calculation, and believe me, you can check, you can probably just do it like in 10 seconds right now. And when you do this, what you're going to get is that this is going to be Z. Okay. So the first pass is good. So if I conjugate X by H, I get Z, which is a Pauli. So that's good. But what about if I conjugate Z by H? Well, notice in this part, so I'm going to just multiply H on here and here. So this is going to be H squared, X H squared, which is X. So again, this is good. What about H, Y, H? This is H, I, Z, X, H. But H squared to identity, so I can stick in like a H squared over here, like as a resolution of the identity. And that's simply equal to I, X, Z, which is minus I, Z, X, which is minus I, oops, it's minus Y. So Y is mapped to minus Y. So we've checked this thing for all like X, Y, and Z, and we found that indeed all of them are mapped into the one of the Paulis. So H is indeed in the Clifford unitary. What about S? This is relatively simple too. So S, first of all, you can see that S actually commutes with Z because S and Z are both diagonal unitaries. So that part we don't need to check. What about SXS dagger? Then what you're going to get is 1, 0, 0, I, 0, 1, 1, 0, 1, 0, 0 minus I. And that turns out to be exactly equal to y. And what about sy is dagger? Well, that's simply s square x is dagger square. But the thing is, s squared is simply z because 1 squared, 1, I squared minus 1. So that's just 1, 0, 0 minus 1. So z x z, which is equal to minus x. So indeed, everything checks out. So h and x, h and s, and the other unitaries which are generated by h and s, they actually constitute the full Clifford unitaries. And this even forms a group. But so for these like single qubit cases, these calculations are pretty straightforward. It's kind of fun actually. But you might think that these things become very complicated if you go to like n qubit. And it turns out that if you know the certain tricks, then it turns out that this turns out to be not so bad actually. So I'm going to tell you how to work these out. So it turns out that if you have like an n qubits, Pauli's, the set of Clifford unitaries are generated by these H, S, and IXYZ, and you just need like one more extra type of gate, which is known as the CNR gate. Some people call it a CX gate. So this gate is defined in the following way. So suppose, let me first note that both of these gates, CX and CZ gates, they act on 2 qubits. So they're not defined for a single qubit. So let's write down some state in a tensor product form over 2 qubits. So I'm going to write down 2 specific states. One is 0 tensor psi, where this 0 is a 0 state, psi is an arbitrary quantum state. And obviously that doesn't cover all possible quantum states because the state of the first qubit was in 0. So I'm going to also specify what happens if the state of the first qubit is in the 1 state. And psi is an arbitrary state. So what it does is that you look at the first qubit, and if its state is 0, you do not do anything. Okay, then the output is exactly equal to the input. But when the state here of the first qubit is 1, then you're going to apply something to this other state. Okay, and what is that thing? That's simply X operation. That's why we call it as like CX. Okay, and this is like defined more generally. So let's say I have some controlled unitary gate, CU gate, where U is some 2x2 unitary, then apply to this state, I do nothing. But if the state of the first qubit is like 1, as you see here, then I apply the unitary U to the second qubit. Okay. So that's the rule. And for completeness, I will also just write down CZ. Like this. Yeah, question?
Oh, sorry, first question. So can you demonstrate how we can write down those controlled in terms of some unitary matrices or tensor product of the unitary matrices?
Like in the two, yeah, so let me think about this. Yeah, it's a good question. So I think I can do that. So So Cx would be something like this. And more generally, Cu would be I guess it should be obvious, but just write it down, CZB. Yeah, so this would be the form. Well, one could also write it down in like a 4x4 matrix, but then like I'll have to specify what the basis is on the for each entries of the matrix. So that'll be more involved. But does this answer your question?
Yes, thank you very much. Yes.
Good. Okay, and diagrammatically, so if I want to write this down, draw this in a quantum circuit diagram, I would do this. So this is the CX gate. And you see this like dot here, right? Like a black dot. Whenever you see a dot, that means that this is the qubit that is controlling the other qubit. So we call this as often control qubit. And this is the target qubit. Maybe it'll be instructive to write down this in terms of colors. So these reds, these are the control qubits. Okay, and the blue, these are the target qubits. And what about controlled unitary? So I should note that for general controlled unitary, this is generally not a Clifford, unless U is very special, but I just wrote it down because I'm talking about control gates. So if you have controlled unitary for general 2x2 unitary U, like you would like draw it like this. Again, you see this dot here, that's again the control qubit. And lastly, CZ is kind of fun. So you would do is that you'll have these two dots. So you might be thinking, oh, like which is the control and which is the target? And the answer is that it doesn't really matter. It turns out that the CZ gate is symmetric under the exchange of the two qubits. So you can verify that this is actually equal to this. So that they're the same. So that's why it doesn't make sense to say that one of them is control and the other is target. So these are the diagrams. But but back to what we're talking about. We're talking about Clifford Unitaries. And just to be clear, this thing in the middle is not a Clifford Unitary. But the question is, how do we check actually that this is a Clifford Unitary? Because to do that, you need to somehow, well, yeah. So let's say for like so for any like a 2-qubit Pauli P, you need to somehow check that P like conjugating P by CX is some like Q, which is a Pauli. And of course, you could actually in principle write down everything in terms of like a 4x4 matrices and check them very explicitly, but that's just a lot of work and it's very annoying. So for these like control unitaries, it's often very helpful to look at their action on the basis states. So let me give you an example. So let's say, so now that I've shown you what the circuit diagrams are, I'm gonna try to figure out what this thing is. So okay, so what's in the middle? This is the two-qubit Pauli matrix. It's really a single qubit Pauli matrix acting on this qubit. And I am conjugating that by Cx. So this is actually supposed to be Cx inverse, but you can check that if you square Cx, it's just identity. Well, why? Because let's say the state of the first qubit is 0. You apply Cx once, you do nothing. You apply Cx twice, again, nothing. What about Cx when the first state is 1? Then you applied X, but then you're going to apply Cx one more time. So then you get 1 tensor X squared psi, but X squared is identity. So no matter where you started, you come back to your original state. So that's why Cx squared is just identity. So like, how would you actually calculate this thing? Like the thing that I see here. Well, I'll just like use the same basis state. Okay, so let's say I start with this state, 0 tensor psi. Then what do I do? First, I apply the Cx. Nothing happens. Then I apply X. I get 1 psi. And then I apply Cx. Then I get this state, which can be thought as X tensor X applied to this state, right? What about the other state? 1 tensor psi. I apply Cx. I get X psi, and then I apply X. Then, okay, I get 1 tensor Xi. I realized that I forgot indeed the tensor product notation here. I hope that's okay. If it's confusing, do let me know. And then I apply Cx. Oh, actually, I'm sorry. So at this first part, I think, yeah, 1 is supposed to stay that way. And then I apply X operation, and therefore it's 0 tensor Xi. Then I apply Cx, and then nothing happens, obviously. So this is equivalent to X tensor X applied to 1 tensor psi. Okay, so for this input state, I apply X tensor X. For that input state, I also apply X tensor X. And I have checked this for, well, the important thing is the setup states of this form and the setup states of this form, they span the entire Hilbert space. And because this relation, because these relations hold for all possible states in the Hilbert space, we have concluded that Cx, X tensor, oops, tensor I, X is equal to X tensor X for the entire set of states. And so this is really a correct equation as an operator. The important point that I'm trying to emphasize here is that these specific set of states that defines the action of controlled X or control U, they're very useful to understand the conjugation property of these unitaries. Good. So okay, so I'm gonna just tell you that all these Clifford unitaries, they can be generated by controlled X and the unitaries that I've shown you here. And it forms even a group. So it's very nice. And so you might be wondering, what kind of useful things can we do with these gates? And the answer is, it depends on what you mean, but if your goal is to perform a computation which is difficult for a classical computer, you're out of luck, because there's this theorem called Gottesman-Canola theorem. And what it says is that essentially what it says at the high level is that simulating Clifford Unitaries is very easy for a classical computer. So more specifically, let's say you start with some product state, all zero state, and then you apply some Clifford Unitaries, like no matter how many, some polynomial number of Clifford Unitaries, and you want to estimate, let's say, expectation value of some observable or amplitude, you name it. And that thing can be done efficiently classically on a classical computer. So what this means is that if you want to do something that is difficult for a classical computer, you have to add in more gates on top of the Clifford Unitaries. And to do something that is difficult for a classical computer, it suffices to add just one extra gate. And that extra gate is T-gate. Well, let me emphasize that T-gate is not the only such gate. There are other gates for which addition of those gates will make the computation difficult for classical computers. But T-gate is like a very natural thing because it's the gate in the second level of the Clifford hierarchy. So I'm just going to give you a brief idea on why that is. So let me remind you, for this to be true, for example, if I conjugate txt dagger, this should be a Clifford unitary. And also ty t dagger also should be in the Clifford. tz t dagger should be also in the Clifford. Okay. So how do we check that? Well, I'm just going to show you. Well, a T is and Z are both diagonal unitaries, so this last part is trivial. I'm just going to show you what happens if I to this first case. So T xt dagger is equal to 1 0 0 square root of I 0 1 1 0 1 0 0 square root of I inverse, and once you do all the calculation, which is not that hard, you get square root of I minus 1, square root of I. So if I pull out the phase factor, I get this thing. And that is maybe to figure this out, but it turns out that this is exactly equal to S times X. So S was this diagonal gate, and X was this thing, and this ends up being that. So up to a global phase, which obviously doesn't, I mean, it turns out that you get like plus, well, it's a global phase, so obviously it doesn't really matter what this thing is. But the point is, if you conjugate X by T, then we get S times X, and we know that S was in the Clifford group, and we also know that X is a Clifford unitary, and therefore S times X is also a Clifford unitary. So indeed, what we saw is that if we conjugate X by T, we get a Clifford unitary. And you can check the same thing for Y as well. And another gate, so just to make sure that we're all on the same page, what did we discuss so far? We had these three hierarchies. So we start with Pauli's, and then we went on to Clifford. And then in the next level, we talked about T-gates. There is a viable alternative to T-gates, which is known as Toefl gates. This is another gate that it lives in the second level of the Clifford hierarchy. And to explain what the Toefl gate is, it'll be easier to just draw the circuit diagram. So the Toefl gate is acting on 3 qubits, and what it does is the following. I have one black dot, which, as I told you, means it's a control qubit. I have another black dot, that's something that's unuseful. So you have 2 control qubits. And you have this this plus sign, which is like basically a not operation. And the gate looks like this. What this means is that I apply this flipping operation, I apply X operation only if both this qubit and that qubit are in the one state. That is to say, so Toefl, which another way to write down is CCX, is if both of the first qubits are in the one state, then I apply X to the third qubit, but otherwise, I don't do anything. Okay, and this is another example of the gate, the second level of Clifford hierarchy. And the reason why this is easy to see is because basically we can run the same trig as we did in this slide. So I told you that when I looked at what happens, so here what did I do? So I conjugated the single qubit Pauli by like a C0 gate. And in doing so, I started with some very specific state, which is like nicer to analyze. And in this case, we can do the same thing. So I can stick in the single qubit Pauli X here. And then what I would do is that I would just write down this expression for 0 psi prime and 1 sine psi prime, where sine psi prime can be any arbitrary state. So you do this and you can just like see what happens. And essentially what you end up getting is equal to I guess if this is not working, now it works. And the end result is basically X times X tensor product C0 gate. And C0 was in Clifford and X is also in Clifford. And therefore, you see that Toefl Gate is in the second level of Clifford hierarchy. Of course, I mean, this alone doesn't establish that, but calculations similar to this establishes this fact. And the very cool fact is that these gate sets that I mentioned, Clifford plus T or Clifford plus Toefl is universal. And let me remind you, universal means that with this gate set, you can approximate any unitary transformation on n qubits arbitrarily well. So you cannot hope to express an arbitrary continuous set, continuous unitary, arbitrary unitary transformation exactly in terms of these things. But at the very least, you can do them arbitrarily well as you want. So for example, you give me your precision that you want. So you say, I want the precision of like 1%. Then I'll give you a circuit which approximates your unitary up to that 1% precision. And if you want your precision to be 10 to minus 10, I can also do that. 10 to minus 20, I can also do that. Okay, so so this is so far what I talked about is the Clifford hierarchy, which I think is an important concept. So let me pause at this point and see if there are any questions. If not, I will, move on to this other part. So this is more of a side comment, but you might be wondering, basically, so in the first lecture, I said some very high level things like quantum computation. We have some algorithms in mind, and then suddenly now we move to like a very low level thing, namely about like quantum gates, like for that matter, a very specific set of quantum gates. So you might be wondering, like, how can you actually translate a quantum algorithms to some like high level abstract description into a sequence of discrete gate set? To that end, like this is more of a side comment, but I should note that there is this fundamental fact in quantum computation called Soloveikitai Theorem. What it says roughly is the following. So suppose you have some discrete gate set, let's call it as G, which we know is like which we know is universal. And then you can ask, if somebody gives me like an arbitrary 4x4 unitary matrix, how can I actually decompose that 4x4 unitary matrix into a sequence of gates in G? Yeah. So for example, let's say I have Clifford plus single qubit Clifford plus T, sorry, 2-qubit Clifford plus T, and I want to approximate like any element in SU4 with some error. Let's say epsilon is like 10 to minus 3. Like, how would I actually do that? What this theorem tells you is that there is a sequence of such gates such that I think I forgot to mention the important part that there's a constant C such that the length of the sequence is at most log C 1/4 epsilon. So C, it turns out to be a number that's roughly like 3. And so what this shows you is that if you're the scaling in the error is basically logarithmic, like not quite like the correct word is polylogarithmic. So it grows very, very slowly. And moreover, this theorem is actually constructive if you read this. So it actually gives you a constructive way of, like, given an arbitrary universal gate set, approximating any unitary in SU2 into a sequence of gates in this gate set. And there's an efficient algorithm. So on the classical computer, this gate sequence can be exactly computed, and one can even guarantee the error. And in fact, for the case of this particular gate set, this Clifford plus T, we can actually do much, much better. So let's say it turns out that we can approximate any gate in SU2 up to an error of epsilon using only a log of 1/epsilon gate instead of like log to the C of 1/epsilon gate, where C is roughly 3. So this problem was essentially solved by these people, Klitschnikov and Mosca, and also Ross and Salinger. And this is like a kind of performance that you can get from a software that was written back in 2014, which they did on a laptop. And so to get a precision of 10 to minus 10, you roughly need like just like 100 gates. And on your laptop, the time to actually calculate this decomposition was around like 6 milliseconds. So very fast. So I guess what I'm trying to tell you here is that when it comes down to the question of like, how do you convert this algorithm to the discrete gate sequence, it usually works in the following way. So the algorithms, the quantum algorithms, usually it's very straightforward to convert those algorithms into a sequence of 1 and 2 qubit continuous gates. So once that's done, what you would do is that you would employ an algorithm like this to convert these continuous gates into a discrete gate set. And the cost that you pay for doing that is like pretty minimal. It simply scales logarithmically with the precision that we're willing to accept, inverse precision that you're willing to accept. So this is what you get. And I would say this is another evidence that quantum computing is digital. Like you have a high level algorithm and you can break it down into a discrete gated set of gates in a very systematic way. Good. So when you read these like quantum computing papers, there will be many cases in which you use some kind of gate or circuit identities, which may seem somewhat mysterious. So some of them will be very straightforward. If it's like a 2x2 matrix, you can just calculate them and verify them very explicitly, but sometimes it won't. So I'm going to tell you a couple of tricks that is very well known in the literature, but somehow like hidden, and they're not quite written down in books. So yeah, so let's go through that. So here is one thing. So suppose, let me first tell you about the controlled unitary. So suppose we are given a unitary in terms of some sequence of gates. Like it's one way to think about this is that imagine you have some unitary over many number of qubits. I guess in this case we have 5 qubits. And we have some big black box, some unitary. I'm going to call it as U. And if we look inside of U, what it does is that it actually is a sequence of like smaller, like 1 and 2 qubit gates. Okay. And the question is, so let's suppose that we know how this unitary is constructed. That's the setup. And what I want to do is the following. So suppose I want to apply a controlled unitary. So I have this extra qubit. So you see an extra qubit here. And depending on the state of the qubit, I want to either apply the unitary or not. Okay. So an interesting thing that you can do, for example, is that you begin with some superposition, alpha 0 plus beta 1. And then upon applying this control unitary, you'll be in a superposition of applying this unitary or not applying the unitary. So how do you do that? And the answer to this is very simple. So what you simply do is that you change all these like 1 or 2 qubit unitaries into their control version. So let me just rearrange them a little bit so that I can draw things in a better way. So how would I do this? So I would simply, for each individual gates, I will change, let's say this, for example, this 2 qubit gate into a control 2 qubit gate. And control 1 qubit gate, control 2 qubit gate, and etc., etc. So why does this work? It works because if the state of this first qubit is in 0, on the left-hand side, you do not apply anything. And on the right-hand side, you also do not apply anything. Yeah, question?
Oh, thank you for giving a chance. So I just wondered whether is there any kind of irreducible gate, like a 3 qubit gate, which you cannot represent by the 1 or 2?
Oh, there is none. So all these 1 or 2 qubit gates can be all represent any 3 qubit gates, and in fact any n qubit gate can be decomposed into 1 and 2 qubit gates.
Oh,
this is,
so
yeah.
Is a theorem? So for example, the Toefl Gate can be decomposed to the 1 and 2?
Yes, I will actually show you later how to convert Toefl into 1 and 2 qubit gates later.
So we just need a 1 and 2 gate.
Yes, that's all you need. And this is proven in Nielsen and Chuang textbook.
Thank you.
Yeah, so just to complete, yes, and if this qubit is in the 1 state, then you apply unitary, that's the definition. And indeed, if this state is 1 state, you apply this gate, this gate, this gate, this gate, this gate, this gate, and all the gates that you apply together, that constitutes U. So you can see that independent of the input, you always get the same result. So this is like a well-known trick to construct a controlled unitary. It's more of a side comment, but I should note that so if you know a description of U, you can always do this. But if you don't know how U is described in terms like 1 and 2 qubit gates, this might be very difficult. And there are some reasons to believe that this is probably impossible. That's more of a side comment. Okay, and here's another thing. This is more of a trick question, actually. So let me preface this by telling you this. So let's say we have Z and X gate. So, and these were Pauli matrices. And when you multiply them together, that becomes IY times psi. Okay. And of course, in quantum states, we really only care about the rays in the vector space, not, well, I mean, what I mean is we don't really care about the global phase. So whether there's I here or not, it doesn't really matter, right? This is equivalent to Y psi. But there's some like subtlety when it comes down to multiplying controlled gates. So let me tell you what that is. So I guess what I'm trying to warn you is the following. So you might be thinking that CZ times CX is actually equal to CY, controlled Y, because Z and X up to a global phase is equal to Y operations. So it's plausible to think that this is actually true. But actually, this is not true. And what it turns out that the correct thing is that CZ times CX is equal to C IY. And this is equal to control I times control Y. So let me draw this diagrammatically. So first I apply, let's see. So one thing about circuit diagram is that the order must be exchanged, because remember, the initial state, like this left-hand side, this is where the initial state is coming from. And if I apply like CZ times CX to psi, psi comes here. So that's a bit confusing, but so that's why CX is here. But in any case, this turns out to be controlled I times control Y. So so controlled Y, this is like pretty clear what that is. Like if the state of this first qubit is at 1, then you apply Y. Otherwise, you don't do anything. But what does this say? Well, let's think about this literally. It means that Ci to 0 psi state is just 0 psi, because the control qubit is 0. So nothing happens. But in this case, you apply I to psi, but I is just a scalar. So this is just I1 psi. So this is really actually equal to applying 1, 0, 0, I to the first qubit. So this is actually equal to that. So what I'm trying to tell you here is that when you multiply single qubit, when you multiply non-controlled qubits, like the non-controlled unitary matrix gates, then the global phase truly doesn't matter. But there are some like mistakes that you can make when you multiply controlled unitaries. And this global phase factor, something that may seem like a global phase factor is actually not a global phase factor. It's something that depends on the state of the control qubit. So that's something that you should be careful about. Good. And good. So now we are almost covered the basics, and we're at a stage where we can start talking about the kinds of objects that appear very frequently in Hamiltonian simulation, which we're going to talk about tomorrow. And what is Hamiltonian simulation? We're basically trying to do something like this. So it's, I'll tell you in more better tomorrow why, but so it's at least, I think it's plausible to believe that if you want to simulate this, you will end up applying some gates of this form, like e to the I Pauli times some angle theta. It's very natural to think about, like, how would you actually implement this in terms of like 1 and 2 qubit gates? So let's say, for example, P is a Pauli matrix acting on, let's say, 100 qubits. Like, how would you actually do this? Like, is it easy to implement this gate or not? And there's a well-known trick for this, and the trick is based on the following fact. So P, let's say, no matter what this P is, as long as it is a Pauli, by the definition of the Clifford group, Clifford Unitaries, we know that there is some Clifford unitary C such that if you conjugate, let's say a Pauli Z matrix acting, let's say, on the first qubit, there's some C such that once you conjugate Z1 by C, you get Pauli P. And that's very useful because that means that e to the I P theta is equal to e to the I C Z1 C dagger theta. And C is a unitary because that's a Clifford. And this is equal to I C1 theta C dagger. So what you can do is that you can ask me how, but I can tell you that given a Clifford unitary, there is a very straightforward algorithm that tells you how to decompose this into 1 and 2 qubit gates. And let's see. And if you have n qubits, the number of 1 and 2 qubit gates to implement this particular C, not an arbitrary Clifford, but for this particular C, can be made to be at most like linear in the number of qubits. And this is just a single qubit gate, e to the IZ1 theta. So even though you might think that this is like a highly non-local gate and therefore something that's extremely difficult to implement, it actually is very straightforward. So all you need to do is apply like a linear number of 1 and 2 qubit gates in the system size. Yeah, and here's another, this is kind of a cool exercise, but if you search the web on like how to decompose a Toefl gate into 1 and 2 qubit gates, you might find some things, but if you stare at the circuit, it will not be obvious like why, like how you would like find those circuits in the first place. So I'm going to tell you about like a general ideas on how to decompose some like a somewhat complicated looking like multi-qubit gates into like 1 and 2 qubit gates. So I'm going to talk about the Toefl, which, as I told you before, is basically this 3-qubit gate with 2 controls. And it's defined as CCX is equal to so only if X and Y are both equal to 1, you apply the X to this the 3rd qubit. And it turns out that this is actually related to something that is slightly simpler called CCZ gate. This is CCX, and this is CCZ. And I'm going to shortly define what CCZ is, but these two are related in the following way. And CCZ is, as the name suggests, it's very much analogous to the CCX, but instead of applying X, you apply Z. Okay, and one can pretty easily verify that these two are the same. The basic idea is that here, the operation that you're applying is X, and there's this important identity that X is equal to H, Z, H. And here, the operation that you're applying is H, Z, H. Z. So you conjugate Z by H, you get X. So that's the rough idea. But it remains, the question remains, like how do you, okay, so I can convert CCX into CCZ in 1-qubit gates, but how do I further decompose CCZ into 1 and 2 qubit gates? Well, here's a trick. So let's look at what the CCZ is. So it has, I'm gonna make the following claim. So the CCZ is equal to exponential of I pi I'm going to make the following claim. So why is this? So let me remind you that Z1, Z is 1, 0, 0 minus 1. So I plus Z. Sorry, I think there should be a minus sign here. So I minus Z divided by 2 is simply 0, 0, 0. So this thing, I minus Z divided by 2, returns a value of 1 if the state is the 1 state. But if it's applied to the 0 state, then it just annihilates that state. Okay. So what is this tensor product doing? It basically annihilates everything except when we have the all the qubits are in the 1 state. Okay. So whatever this thing that is so if all the qubits are in the 1 state, then I get the phase of -1, because then I have e to the I pi times 1, and e to the I pi is -1. But in any other cases, what I get is e to the I pi times 0. So I'm going to get 1. So that's exactly what CCZ is. And here's the cool part. So the thing is, this identity and z's, they all commute with each other, right? So what you end up getting is e to the I pi 8, basically 1 over 8, like I minus z1 minus z2 minus z3 plus z1 z2 plus z1 z3 plus z2 z3 minus z1 z2 z3. And I already established how to decompose these like e to the I p theta into like a 1 and 2 cubic gates. So you have all these terms commute with each other. So you just re-express this as a multiplication of like 1, 2, and 3 cubic gates. And the 3 cubic gates you can further decompose into 1 and 2 cubic gates. So that's how you actually end up getting the circuit decomposition that you can find on the internet. Okay. All right, so sorry if this was too fast. Maybe it was too fast, but I wanted to tell you about the basic facts that people use in these quantum circuits. So we learned about universal quantum gate sets and how people actually convert algorithm into these gate sets, and also various circuit identities. So what I can suggest to you is to work out the examples that I showed you today. I think that will probably be very helpful to understand the literature. Okay, thanks a lot.
Thank you very much. So we are a little bit behind in the schedule, but do anyone has any quick question? Yeah, Professor Kim, if it is okay, could you maybe send me the updated note with your writing?
Okay, yes, I'll do that. Yeah.
Yeah, student already access to the previous notes, but it might be useful to have the updated one. Thank you.
Okay, thank you.
Okay. So if there is no questions, why don't we conclude the morning session, and then we will come back to the quantum computing lecture tomorrow in the morning again. Thank you very much, Professor Kim. We will see you tomorrow.
Yeah, thank you.